Hi everyone. Can you guys hear me? We have 0 viewers. Oh, there we go. Let me just pop out the chat. Thanks for asking. I'm doing better, but I just had a meeting. It was kind of an important meeting. I had my camera on and everything, and it's an hour long meeting. Well, no, actually not an hour long, about 45-minute long meeting. But by the 45-minute, I was already like twisting to the side. So I think I'm gonna keep my camera off and just kind of try to like lean back as I write, because it is still a little bit difficult to kind of be awake and teach properly. So yeah, yep, you'll just hear talking voice without a face. Uh, but yeah, I should be okay. Like I said, this is the first of 2 classes. The second class is the one that will be interesting and see if I can handle. So let's go ahead and update this that we're only going to be talking about hatching today. But I did leave it up here just because I wanted to see if anybody had any questions about heaps or heap sort. I know that we pretty much covered most of it last time, and then you'll watch a video on it. So you should have, for the most part, be good to go now with heaps. Uh, for assignment 9, is there a sample output you want us to follow? Oh, yeah, I did actually see that on Discord. I was going to try to respond to it, but I wanted to check first what exactly that entailed. So here, let me open that up really fast and see, and I can tell you better. I do think that it won't really be easy to show because if I remember correctly, where's it at? Here we go. Okay, so this is this one. Yep. So this is the heap one, and this is part 1 of 2 of an assignment. So make sure that there is going to be another Edge of Tomorrow themed assignment that's coming later. Okay, so here's what I recommend. I'll try to pull up some sample output, but if not, feel free to share. Oh, assignment 9. When is assignment due right now? Oh yeah, it's due November 7th. I Oh yeah, because of my sickness, I had to delay my flight back. So now I'm gonna fly back on Thursday, Veterans Day. Uh, yeah. So that won't affect anything. I'll just teach class from here. But yeah, okay. For now, I'm going to move the heap assignment to the 13 and 14 due date. That way, you have more of a gap. And feel free to share sample outputs if you'd like. But I'm just trying to remember if it'll help you because I remember they might be different. Yeah, see what happens is when you generate the shifts, they're going to be different each time. So that's why you didn't really get an output because it's going to be different each time. But you're more than welcome to share it. Uh, Obviously, just beware that everybody's is going to look slightly different because it's the sampleness. You know, like it's going to be random. It's kind of like the first assignment. You know, the ship names are different, so it's going to be different each time. And depending on the priorities that you assign, it'll look even more different. So, yes, you're welcome to share it. Just beware that they will be different than yours when you run it because they could be doing a different way of randomizing things and the priority things. The only thing that's going to be the same is going to be the top of the heap, right? But like even that has like similar, there's similar priorities as the J squad stuff. So just beware of that. Don't get confused if you shift are not exactly in the same order. Okay? Uh, but yes, you're more than welcome to do that. Other than that, there isn't like a particular, this isn't as strict as the other ones where like you have to have an A after a B after a Z in terms of like the formatting. So yeah, you're more free on how do you want to format this because of that. Okay, and that's because there wasn't a need to have you do this very specific formatting. It's not like 202 where we need to run code grade on it to grade it, and it has to be like to the dot. So yeah, but yeah, feel free to share it. All right. Any other questions on the assignment stuff? Oh, big thing, the test, right? Uh, Test. So the second midterm it would be a week from today, and what I wanted to ask you is what the cutoff should be. So the test is not comprehensive, the second test at least. It's going to pick off where the other one left off. So basically, the test is all about trees because if I recall correctly, the last test ended with the sorting. So you're going to have all of the tree algorithms that you did, right? So traversals, building the trees from the traversals, ABL trees, and heaps, right? These are like not optional. Like you are going to have that in the test. But now my question to you is if you'd like me to also include hashing or to defer that to the final exam. That now before you completely answer that, do think about the following though. If you do the hashing stuff now, at least you get it out of the way and it's fresh in your head, in your mind, not your head. But if you wait until the final, then it's going to be a month, because we're hashing is one of those things we're going to talk about and then we're going to move on. We're never going to see it again. So if we do include hashing, at least you kind of get it out of the way while it's fresh, and you don't have to remember all these hashing stuff, uh, like different ways you do hashing. So typically I include it, but that would mean that you know today's content and potentially next class content is there. So all right, so now you're more than welcome to answer. In fact, you know what I want to do is I want to do a Twitch poll. Uh, that way it's more democratic and people that can vote anyways. In fact, I think even people who are not subscribed can vote. Like they're not like like logged in. That's what I mean. Not subscribed. That would be very biased. But yeah, so I'm gonna go ahead and run that poll. What happened to my poll system? It used to be here. Manage poll. Clip that. Okay, here we go. Add. I almost clicked on run a 1 minute break. That would have been bad. All right, create a new poll. Okay, so include hashing in midterm 2, November 11th. The answer is yes or no. Allow additional votes, bits per vote. No. Duration 1 minute. I will do 2 minutes just in case people are in the bathroom or something. There we go. So, yeah, go ahead and vote on your poll. And the final, no, no. So the final was going to be comprehensive, but it will not be comprehensive anymore. It's just going to be on the third part. When I do it in person, I do it comprehensive, but online, there's not really much reason to make it comprehensive. Uh, because I mean, like, yeah. So, yep. Anyways, while that poll happens, I can actually show you the results. Yes, I will have the time window open for a time range, just like the other test. That's not a massive time range though, but yes, it'll be the same. It'll be the exact same format as the first test. Okay, I think if I do this, you can see the poll live. trying to see if I can get the numbers in there. There we go. You can kind of see them now, right? I don't know, distracted with the tabs on top, but there you go. Okay, so it does look like, unless there is some last minute drop of votes here, like to change this outcome, that it does. But I mean, you never know, right? So let's just wait and see. Okay, so there you go. That is the one that won. All right. So I guess that means that we are going to have the hashing. Okay. Well, then let's get going on the hashing so that we could make sure that we get through it. Right. And obviously, if we don't get through the entire thing, then whatever we do get through is what's on the test. But yeah, we should be able to finish it though. Yes, November 10th. November 10th. November 11th is Veterans Day. So, yes. Um, that is a day that hopefully I'll fly back. Unless I fail a certain test. Uh, okay. All right. Cool. So now the video that you watched already did introduce a little bit of hashing, right? Just please confirm with me if that is wrong. Uh, yeah, I'm not surprised it's buffering. Let's see if I can fix that a little bit, though. Can I close here? I'm just checking to see if there's anything that I can close to kind of help out. These are all static pages. Oh, I guess I can close the Twitch thing now that I don't have it open. That'll help a little bit, if anything. Okay, there we go. So yeah, go ahead and confirm with me that you did get a little bit of an introduction, not into hashing, but at least at direct access tables on the video. Uh, that was the example I gave with the phone number. Okay, because otherwise I don't need to go over that example again. And just so you know what I'm talking about, let me go ahead and put a picture here. At least I'm trying to I'm trying to copy and paste this massive thing. Copy. Okay, there we go. So this is what you probably saw in that video, right? We don't need this anymore. So someone in chat, I just want to triple check that this is the example that you saw that I introduced, right? Okay, yes, thank you, appreciate that. Okay, great. So the concept behind this was that we were trying to access phone numbers and like what you want to access it quickly in that O of 1 time. That so far no algorithm that we developed can get that O of 1 access time. So far the best we've done is log n. Like we have an AVL tree, we can access any number in the list, or just simply check whether it exists or not in the list in log n time. We could also do that on a sorted list using something as simple as binary search. So log n is good, but it's not O of 1. O of 1 is at constant time. Constant being the ideal because it is super fast, right? So I proposed the idea that if we're trying to store the names of people's phone numbers, why not make the phone number itself the actual index of a massive array of size 10 billion, right? That would be from phone numbers all zeros all the way to phone number 999 How many times did I say there? 999 right? So that's the range of numbers. If you do that and you get this 10 billion right here, then the phone number itself becomes the index, and we know that arrays in C++ and the way they're implemented in memory, if you just put in the phone number itself as the offset of that original pointer that starts the array, whether it's dynamic or static, then you can access things immediately. And so you achieve that O of 1 time. Now that sounds very cool, but in practice there's a catch. And the catch is you need space for all 10 billion possible combinations. That's a lot of space, even for just storing a string. And so that is a solution to a problem. And that really comes back to what we said in the beginning of the class when we were talking about asymptotic complexity and we were talking about space and time. And I said, look, the majority of the time, we are going to care about time complexity. And we're going to say, I really want things to run fast. I want to be able to access things quickly. I want to be able to store information quickly. I want to be able to retrieve information quickly. I want to be able to delete information quickly. And secondary to all of this is going to be space. Sure, if it allows me to access things faster, you can take more space. That's okay. I got a lot of space nowadays. And for the most of the semester, that is kind of what we've been thinking. We look at things like quicksort and ABLs, and it's nice that they don't take a lot of space, but even if they did, we would just shrug and be like, oh, whatever, I got that 4 terabyte SSD, it's all good. Okay, sure, nice flex, but at the end of the day, hashing is going to be the other side of that coin. Hashing is when like somebody comes to you and says, "Oh, really? You don't care about space. You just want speed?" Sure, why not? Let me go ahead and throw to you this direct access table system where very quickly you can go ahead and take that 4 terabyte SSD and fill it up with pretty much 99% blanks and then the 1% with actual valid data. However, you do get that O of 1 time. And you're like, well, okay, now it becomes a problem. So that's where hashing is going to come in. Hashing is going to try to provide you with the ability to not have to waste so much space, but still have almost that O of 1 time guaranteed. And it doesn't matter, whether it's 4 terabytes or 512 M2s. And M2s are great. I mean, 2 terabyte M2s are amazingly fast. But it's not going to matter there because it's like the more you give, the more you want. And so you come and say, I got a 512 gig NVMe, and then I come and say, guess what? My phone numbers are now 20 digits long, and I only still use about 1% of the actual number. So you try to store that in, and that's completely useless now, right? So, okay, that sets the table of what's happening, and that's kind of where this came from. Right? And I guess we did this calculation. I don't know. Hopefully this was accurate. But we said it would take about 40 gigabytes just to store the phone numbers, which is like insane. Like that's a lot of space for something as simple as a phone number. Uh, so yeah, kind of scary. Okay. Obviously, not think about storing more than that information. Already, if you're storing times 10 this information, or I say times 20 maybe, then you need a terabyte almost. Okay? All right. So what I propose now to do is the following. Let us take our phone numbers from the previous example and copy and paste them. So we got all these numbers. Actually, I don't. Are they the same numbers? Yeah, they're gonna be the same numbers. Okay. And let us try to do the following. So we know that, of course, if we store the full phone number, we get that O of 1 time. But why not, instead of storing like the entire phone number per se, or at least using the entire phone number as indexing, why not just use the last 2 digits? So the ones here that are in orange and red. Now, why would we want to do that? Well, because if we do that, we only need an array of size 100. Sure, we only still have 6 phone numbers, and technically speaking, you could store this in an array of size 6, which is way less than 40 gigabytes. But this is a nice compromise. If we store this in an array of size 100, sure, it's not size 6, but it's also not 40 gigabytes or 10 billion of size, right? Now, if we do that though, there is a catch. And that is the only way that this is going to work is if there is no collisions between them. Now, what do I mean when I say collisions? Collisions means that if I'm taking this value here, so like this address right here, and I'm only going to take the last two digits and use that as the index of an array of size 100. So here we got array of size 100. I'm going to say, well, that's going to go in slot 13. I'm going to put Rachel's names there. Okay, and you could also store the phone number here since now you're not storing the entire phone number in the as the index itself, so you can't really retrieve it. So if you want to, I mean, if you're looking up a name by a phone number, you know what the phone number is, right? So you don't really need it. But say you wanted to store it anyways, that's okay. We're still not going to be at massive space now. So you could store something like this in that index. And the point is that you could retrieve this information or you can find it in constant time if all you do is you look at the last two digits. But the catch is none of the phone numbers here have the last two digits that are duplicates of each other. So when would that happen? Well, let's just say that we had somebody whose phone number was 722-111, and then it was like 1222, and this was I don't know, Steve. All right. So in this case, this is an issue in our little theoretical sort of solution. We can't use this little indexing system anymore because that collides with Jane. What that means is that if I'm trying to store this in this array, well, I can store that in 85 for Nick, and then 17 for Kevin, and 29 for John, and 22 for Jane, and I guess this is the nameless mystery person. I don't know, and so on. But the problem is that when we try to store Steve, we already find that that slot has Jane, so we overwrite it. And that's not good because we are losing information, or we just don't overwrite it, but then we're like, what do we do with Steve? Right? So the idea of taking a bigger number and just using part of that information as a way of deterministically deciding somewhere in this array that's smaller is what's known as hashing. And that's kind of the source of hash tables. And what you gain from that is that you can still achieve this O of 1 access, retrieval, and deletion time as long as there's no collisions between your deterministic computations of that hash function. That is where the trick room is of this. That's the not easy part of the process because in this case, my solution is as simple as just taking the last two digits. Now, could I solve this dilemma of the Steve and Jane situation? Sure, I could take three digits now, and sure, I'm increasing my array from size 100 to a size 1,000, but at least I solved the issue. At least until I get another person who has the last three digits the same. So you might be asking, well, then okay, if this solution is only going to work depending on the data, and we know that like there's a very easy way to come up with an example that's going to break it, then is hashing actually useful? And the answer is, well, yes and no. It depends. It depends again on your hash function. Your hash table is going to be as strong as your hash function, and so that's kind of what we hand wave a little bit in the class. I'm going to show you what hashing is and hash tables and collision resolution and all these wonderful things. But what I'm not going to really show you is how to build a good hash function. For that, you would have to take probably like a cryptography class or probably not even analysis of algorithms covers that. And so I do have on Canvas though hello. I do have on Canvas though a link to something about cryptographically secure hashing, which kind of gives you an idea of what are the good things a hash function should have to make it a good hash function, a secure hash function. That's another thing. We're not even talking about security yet, but as you might have guessed, hashing plays a big role in security because one of the great things about hashing is that you take information and then you perform mathematical computations on that information to decide the index on where to store it. But now, what if I say instead of getting an index back, you get a mixture of letters and numbers, or just actually just numbers, but like hex or something, and these numbers represent what you hashed in. And then instead of storing the number or the data that you hashed in, you store the output of that. And you know that the only way to get this output is what you because of what you fed in. And that's what's known as a hash value. So like a password. So when you go and log in onto a social media website that's about to get hacked or something, uh, what happens is they don't store the plain text password. They feed it to this magical hash function. So you got your password that's like let me in is your password, and then you feed it into this magical black box, and then out of that black box comes in a bunch of letters and numbers. And then somebody else comes in and feeds it another password. These people were more secure. Their password was 1234 ABC because these are clearly the best passwords ever. They feed it into the black box and they get some other numbers that are like that. And so the important thing is that every time you feed this, you get this. And every time you feed this, you get this. That's known as a deterministic hash function. This is your hash function. You always, always, always want your hash functions to be deterministic. Okay? If they're not deterministic, by the way, here's a hint. If you put your password on Twitch chat, it hides the password and you only get asterisk. Here's me trying it. See, my password's hidden. Hopefully you don't actually try that. And then, it becomes that meme. I think I saw that on Reddit or something. But yeah, so yeah. Anyways, the point is that that's determinism, and that's something you want. Because here's the thing: you could say like, oh, I'm never gonna have, and you want these to always be different too. That's known as collision resistance. Here, let me actually give you the link of that so that you can check it out on your own time as well. I mean, I'm gonna talk about a little bit about it, but it's good to know too. Here you go. So that's the link on Canvas, and let me very quickly share my screen so you can see that. That's what I'm talking about here. Oh, that's very sad. The picture broke. Does that mean the link broke? No, the link is not broken. That's cool. Okay. So you can check out that link, but this is kind of like the TLDR version of that, so the summarized version of that, of what a hash function should have. So the deterministic is what I'm talking about. That again, you know, you want to every time you feed it the same input, you want to get the same output. Because if you don't do that, if it gives you different outputs every time, that would be the same thing as you just randomizing the output. And if I'm saying, okay, every time that I feed it this phone number, I want to get Rachel's name back. And if I randomly get Nick's name back, that's a bad thing. Okay? By the way, what is the mathematical conversion of what I have here, of just taking the last two digits? If I had said to you, write me a math formula that's going to take any phone number and give me back just the last two digits as a number, what would you do? It's pretty easy, actually. I mean, it might take you a second to think about it, but it's pretty easy. So I'll give you a second to think about it. And the answer is, that's right. You got it. Very good. is you take the phone number, which we're going to consider X, and then you take a modulus of that, and you do 100. Or if you're going to do 3 digits, so this is for 2 digits. And yes, if you do 3 digits, then yes, do 1,000. And this is normally how you write your hash functions. You say h of x is equal to x mod 1,000. Okay? So yeah, that's uh, that's all there's to that. That's your hash function. So whenever we're talking about hash functions, it's just math. You do math on it, and the math you do is whatever you choose. But the point is that this is deterministic, right? There's no rand here in code that's gonna screw things up. Okay? So again, the class, this is the only time I'm really going to tell you about how to make a good hash function, because the rest of it is just going to be about how hashing works. And again, you have to take a cryptography class if you want to know more. But here's another thing that's important, and it comes from that list that I linked. And that is going to be property number 2, which is a quick computation. So remember, why are we trying to do this? Like, what is the purpose of trying to do this? And that is to make fast. And that's actually both when you're dealing with passwords and security, but also when you're using hashing as a storage solution. And that is, you want to be able to access information fast, right? That all of one access time. You want to be able to feed in the phone number and then immediately get back the name. How do you do that? How do you achieve this power? And well, that's good hash function. And the good hash function is going to be a function that can be computed fast. If you have this super insane complicated formula here that makes you never, it's deterministic and it avoids collisions and everything, but it takes like 10 years to compute, then this is useless. From a password perspective, the same thing. If you log into your social media website with your password and it takes 1 hour to actually check if your logging is correct, then that website's probably gonna not work out very well, right? So it has to have that quick computation. So it's very important. It might be trivial to think about that, like, oh yeah, I mean, of course you want it to be fast, but like, it's easy to overlook. Okay. The other property is a little bit trickier to understand, but let's just try it out. So we got pre-image resistance. Uh, let's kind of just read this first, and I'll explain what it means. So given h of a, so given the hash value, it is infeasible to determine a. What this is saying is the following. Right now, if I if I say to you, okay, uh, I got the hash value of 13 out of feeding it to this function, and I ask you, what's the phone number like that you started out with? You might go and say to me, well, I don't know. I mean, it's kind of impossible because there's a lot of phone numbers this could have started with. But what you can tell me though is that the phone number does end with 1 3. Or you might not be able to tell me that immediately, but you could deduce that because the hash function could be public. And so you could feed in a bunch of numbers here to experiment. So you could feed it, well, I'm gonna feed it phone numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you feed it like the first 1,000 numbers. You start to see that pattern. You're like, oh, all the numbers that I'm feeding, it's taking the last 2 digits of that and it's actually just returning that. That's bad. That's bad from a security perspective because if I'm able to feed it, if I'm able to see a hash value for a password, so if I'm able to see these values, like there's a data breach, and these values leak out, and I'm able to see them, and I can reverse engineer my way to your passwords, that's really bad. As your data, that's a really, I mean, it's already bad enough that you have a data breach to get those. But if now you can get the plain text passwords, then then you're screwed now because I'm gonna copy and paste that into Gmail and get into your Gmail address and your bank accounts and bad things, right? So that's what we mean by preimage resistance. That we don't want to be able to reverse engineer it. So this hash function has to be complicated enough that you can't work your way back. Okay? Now, for storage purposes, it's not as important because you're not doing it securely. For cybersecurity purposes, it is 100% important. Okay, so this is the one exception where I'll say, sure, if your hash function works really well in your projects for storing data, retrieving data, and whatnot, and you don't care about that reverse engineering, then you don't need that preimage resistance. But for security purposes, you need it. Okay, and this kind of goes into the next one. One way that you can make pre-image resistance actually good is to have the avalanche effect. Now, what is the avalanche effect? The avalanche effect is kind of shown here. These two passwords make completely different hash values. And if I went ahead and said, well, I'm going to submit a password where it's let me in, because, oh no, my let me in password showed up in a data breach. What do? Let me just uppercase a letter, and now it's a new password, so nobody will ever figure it out. No, they'll figure it out. But the point is that you do that, and then you feed it here, and the result of this, you see that the hash value is like this. This is bad. This is what will be known as the avalanche, not as failing the avalanche effect. The avalanche effect says that even if there's a tiny little change in your initial input to your hash function, it should completely change your output. This is actually good for both security and storage, because when you have collisions, and this is something we'll see a little bit later as we learn more about hashing, but like when you have your data, you will typically find your data clusters. It clusters into sections in your hash tables. Like for example, in the practical point of view, this is like your 702 area code phone numbers. There's a bunch of them, and maybe there's not that many phone numbers that have 725 because it's a new number, right? So but you still see clusters there. You don't see that many maybe with 701 or 700 and so on. So the next cluster is maybe whatever area code is, like 696. I don't know. Whatever the next like legit area code is. I think 700 might be a legit area code. Uh, yeah. So, anyways, the point is that your data tends to cluster, and the avalanche effect is really good to avoid that clustering, because if you have two passwords that are identical, but they create completely different hash values, they're going to be storing completely different parts of your hash table, and that's going to take this clustering and basically even it out, make it more like even throughout. Okay? That's a good thing. That's something that you want. And from a security perspective, it's also something you want, because this is bad. In this case, if you see that both of these are almost identical, you're like, oh yeah, I mean, these, if like somebody knows that this let me in is this password, and then they see another hash value that looks almost identical, that starts to give them a hint that the original input might be similar, and it is. There's just one letter difference, and so they might be able to guess it. If instead you have the avalanche effect, this thing will look completely different. Well, like that. That's a completely different number, even though these two are almost identical. Now that's hard to do from a hashing perspective. Like you got to do your formula to achieve this with your math formulas. It's not easy. Again, that's why we don't cover that kind of detail. It's a crypto security class. And again, the algorithms that were posted on chat, MD5, SHA-2, these are all algorithms that actually are relatively effective at this, although MD5 has been broken. They have been able to crack some of these properties, so it's no longer cryptographically secure, but it's still secure for verifying whether data has integrity or not. So yeah, that's the avalanche effect. You want things to completely change the output, even if you change the input slightly. Okay? The final thing, it brings back to this keyword I keep using, which is collisions. Collisions are when you feed in two different values to your function and you get the same result. We don't ideally want that, because that means it's going to go into the same spot in the table. I am going to show you how to handle that from a storage perspective. From a security perspective, you just never want it to happen in the first place. And so that's why this says collision resistance. When something is collision resistant, it means that it is very unlikely that it's going to happen. In fact, It is practically impossible or infeasible, as I used earlier, that keyword. Okay? So that is basically saying that it is very, very infeasible that we have an input H of A and an input H of B, and that they both give you the same output X or something. Okay? So yeah, crash proof. Yeah, you can call it that as well. So you want everybody's hashing value to be unique. But again, this is all easier said than done. These people that develop these algorithms like SHA-2 or SHA-256 are hardcore. Like, my respects to them, because it's not easy to do this stuff. And SHA-256 isn't particularly fast either. I mean, it's fast. No, don't get me wrong. It is extremely fast, but it's not fast enough where you can just like use it to store normal data. For storing normal data, I think that sometimes you have to make compromises. Okay, so yeah, no, it doesn't go against property one, because that's the cool thing about it. It's deterministic. So what I'm saying is that two inputs should give two different outputs all the time, and then that two inputs should not give the same output, but they should still be something fixed. So like, if I feed it 22, I should get 23 back. Let's just say that. And if I feed it 21, I should get 24 back. But I should never get like feed 28 and feed 29 and get 30 back. So you're still fixing that connection between the in and out. So I'm saying, okay, into my black box, which is that hash function, if I feed it this, I get this. If I feed it this, I get that. If I feed it this, I get that. These are all different, but they're the same different. So like, this will always be linked to that. Maybe this will be linked to this one, and maybe this will be linked to that one, but they're always the same links. It's just that they're different. You never get a collision. That's collision resistance. And by the way, in theory, you should be able to find a collision, because there's an infinite number of inputs, right? But there's also an infinite number of outputs, but it's very unlikely that they're perfect. But it just becomes like super, super, super hard and very unlikely. Like, you're better off winning the lottery than trying to find a collision. That's where security comes in. That's why they say, the faster computers get, the more brute forcing we can do. But even then, like, trying to find a collision would take longer with current computing than like the length of the universe before like the universe ends. So yeah, okay. So that's your introduction into crypto security. That's all we're going to talk about for that. Now we're going to go back to good old just basic hashing and just kind of explain that and all of those things. Okay. So let's start by just defining a couple of things. So normally I do it the other way, by the way. Normally I talk about security at the end after I talk about hashing. But I thought this time around I would start with security stuff to kind of maybe interest you, and then do hashing. So maybe at the end I'll ask what people prefer and just pick that. Uh, so what quantum computing? So one of the things that hashing uses to make it secure is factoring. And math factoring is a cool thing. And quantum computing is really good at this factoring stuff. So yes, there is a certain degree of risk that quantum computing can potentially crack some of these security algorithms, which can cause issues. But it's going to be a while before any of that takes practice. Although I do keep hearing about it. If you're interested on that, look up. I believe it's called primacy. I think that's the word. Uh, what that means is when the day that quantum computing beats your traditional computers at a math problem. That is like an actual practical problem. And that's when they say we have achieved primacy. You keep every time you like every 2 or 3 years somebody comes up with an article saying, "Oh yeah, we just achieved primacy." Uh, no, not privacy, but primacy with an M, like primate, but primacy. And I think primacy is the term. Actually, let me Google that just to make sure I'm not thinking of a different term. Primacy computer. Yeah, it is called, yeah, here. Quantum primacy is the goal of showing that a programmable quantum computer solves a computational problem that is currently infeasible or non-quantum or classical computer result has takes, yeah. So yeah. And you can see that like literally like I actually did look at this article about yeah, but a week ago that they were saying that like the two Chinese teams reached primacy, but like you will see this stuff happen like every 2 or 3 years, and it's not going to be a thing where it'll be like very obvious like we've done it, because people keep claiming they've done it, and it's kind of hard to see which one's true or not. But like it's been happening for the last few years, so yeah. But anyways, that'll be very interesting to see in the coming years. You know, maybe one day they'll have a quantum computing class at UNLV. I did have the blockchain course. We did have a guest uh, faculty from South Korea come in and talk about quantum computing um, some years ago, and that was pretty cool. So yeah. Okay. Anyways, so hash functions. Hash functions, I think you get what the point is, what they are. Hash table is just a table where you store your information that you just hashed. So your phone numbers are storing in that table. That is a hash table. Hashing typically provides O of one time. So we want that, you know, compare that to ABLs that provide log_n for your access, your retrieval, and your deletion, or heaps that provide that log, you know, heap sort and log_n, uh, or linked lists, which provide linear time for accessing potentially. Arrays that are sorted can provide you log_n time if you use binary search, but a normal unsorted array takes n time. So obviously this O of one time is like way better. Okay, so here is the formal definition of a hash function. Hash function maps a number or a string to a small integer that can be used as the index to a hash table. And you can uh, you can watch the video that I have that follows the one that I linked last time. But I am going to take a picture from there just because it's really pretty, if I may say so. Kind of self-compliment is weird, but yeah, I will say that's a pretty picture. And again, just shows you the same thing I'm talking about. So we got a bunch of numbers we're inserting, and there we're saying where we're storing them. In this case, again, we're just doing modulus 10, and as you can see, that's where things get stored. Here's what that would look like in code, is literally just a function that is h of x returns x mod 10, and that's all there's to it. And for retrieval and access and modify, what you do is you want to check if something is found, is you feed it to the hash function again, it returns to you an array index, and if in that array index the item is found, then you can say that yes, it's there, and then you can either delete it or just simply say that it's there, or you can edit it, do whatever you want with it at that point. Otherwise, for example, if 99 is there or not, you feed 99, you hash it here. In this case, we're just hashing by 10. We get 9, we see it's empty, so we say it's not found, right? So again, you can see the basics. I have one more picture to show you, and that's for collisions. Again, this is all stuff that I already talked about right now, but nice to have pretty pictures. So for collisions, what we got is basically, again, the same little array that we created here. Let's say that we try to insert 21. 21 gets hashed. This is mod 10, so it just gets spot 1, so we put 21. But then we insert 51. 51 gets hashed. We get also 1, and then bam, collision. So again, this brings up a lot of questions. Okay, we don't want collisions. We already established that. But what do we do if we get a collision? Well, if we're in a security perspective, we are basically screwed. But we are talking from a storage perspective now. From a storage perspective, there's a lot of things we can do. We can overwrite. We can just not insert. We can give up. Well, that's the same thing as not insert. So yeah, I guess it's really the two choices: either overwrite the data or not insert. Well, actually, no, there are other choices, and that's what we're going to talk about. But right now, these are the only ones that we can really think about. But in these, the issue is both of these involve losing some piece of data, right? And so there are what are known as collision resolution approaches here. So yeah, you can just give up. You're taking the test and you're like, dang, what do I do now? I don't remember how to do collision resolution. Well, I guess we take the uh the give up approach, right? So yeah, okay. So there are two solutions that I am going to talk about. The first one is known as separate chaining. Well, actually, you'll notice that these, well, this is not the first time around, but I hope by now you've noticed that some of these things have different names to them. Actually, well, no, that was not the 202 class. Yeah, that's mostly the 202 class. When I'm telling them, like, well, you know, base class versus like derived class. The base class is called the parent class and the child class, or the super class and the subclass. So yeah, that's more of a 202 thing. They have like 50 different names for different things. Here we don't have that much of an issue, but here we do have that because there are multiple names for collision resolution. The other one for the same thing, basically. So one of the ones that I want to talk about is known as separate chaining, but that has also the name of close addressing. Okay? So what is close addressing or separate chaining, and how is this going to solve our problem? Well, first let me go ahead and define what separate chaining or close addressing mean. I personally like the separate chaining one because that one's easier for me to remember what this actually is about. And so what separate chaining is what you're essentially here. Forget about the definition. Let me just show you what we're going to do. What you end up doing here is instead of just giving up, start making a list right here. Oops, sorry, very twitchy. Start making a list of numbers here. So you're like, oh, the 21 needs to have a friend there. Then just throw it in. So you, as the name implies, you chain the numbers together, or you chain whatever your hash value is together, and just store it there. No, hash value is not the verb. Chain the original input there, because that's what you're storing. The hash value is the one. So you make a list essentially. Now, how you store that list is going to affect things a lot. So let's just start about the most basic way of how to store a list, which is just, well, just dump it all together. And if you want to make it dynamic, you just make a linked list, right? So let me go ahead and bring in a couple of numbers here. This time I'm going to just come up with them myself and use the same hash function. Okay, so we're going to use it mod 10. Again, we're using the most basic hash function possible because that's not really the focus of this, but as I hopefully you appreciate, hashing can be very, very fancy with a lot of very fancy computations. Definitely not mod 10 in the real world, but mod 10 here because I don't want to think too hard to compute these things. Okay, so we're going to throw these numbers into our hash table that's using this formula. Okay, and our hash table is going to be, by the way, there's something important that I should bring up. How big do you make your hash table? Well, that's going to depend on your hash function. Let's think about it for a minute. This hash function goes from, what I almost spoiled it, but this hash function has mod 10. So, regardless of the input, what are the range of outputs that it can give me? Well, the range of outputs are, if I feed it a 10, 10 mod 10, or 0, it's going to give me 0. Could also give me 1 if I give it something that ends in 1, right? Could all the way to 9. And then if I feed it a 10, it's going to go back to 0, right? So the range of numbers that you can get from this hash function are 0 through 9. inclusive. Could I ever get any other number other than these? The answer is no, unless of course I change the hash function. And so that should make you aware that you should never make this hash table bigger than 10, because that's, and with this indices, because that's the only indices that you will ever use. You could make this hash table size 100 and you'd only be using these 10. So like why, right? And so when you're picking your hash table size, you should pick a size based on the amount of data that you have, yes, but more importantly, based on what range of numbers your hash function can give you. If you have a hash function that can give you the number 15 because you're doing mod 16 or something, and you only pick 10, 10 values, you're going to go out of bounds. Well, there wouldn't be a segmentation fault if you put 10 into a 100 table, but there will be segmentation fault if say you put 100 mod 100 into a table of size 10 and you fed it like, or and you fed it like 28, because that would, the mod 100 would still give you 28, and a table of size 10 would make you go out of bounds. So that's an important thing to keep in mind. I'm getting winded up here. Okay. All right. So let's just plug in the numbers here and kind of go with it. All right. Let me kind of like lean on my side here. All right. So we're gonna put 42, which mod 10 is gonna give me 2. So rather than keeping the information on the array itself, now I'm going to do a different approach. And this is part of the separate chaining approach. Don't keep the data in the array. Make the array a fixed size, which is kind of like a size of a pointer, basically. And store the data on a linked list that the pointer points to. And the other ones can point to null in the meantime. And so on. Okay? I'll use a dot for null. Okay. So now we're going to feed it 8. And it's going to go there. Oops, sorry, I meant out here. Now 21. 21 hashes to 1. There we have our collision. So before we would give up, but now we're doing separate chaining. In the case of separate chaining, you're just going to append it to your ongoing linked list. Oh, sorry. No, what am I saying? 21. 21 goes here. There's no collision. Sorry. I thought it was 22 for some reason. Well, now we see that with 32. 32 is a collision because 42. So that goes here. Now, how you insert that is up to you. On your linked list here, you can put it at the end. You can put it at the beginning. Just keep a pointer so you can still insert an O of 1 time. So you're still inserting an O of 1 time. No problem there, as long as you keep your pointers right. 55 and 22. 22 is also a collision. So it goes there. So here we have our data. Now, I said that with the hash table, you get O of 1 insertion, removal, and access time. However, with this collision issue, it's no longer the case. It turns out that if we're trying to access 22 or 32 or 42 technically, when we go in there and we hash, we're no longer getting an independent value back. We're getting a list of values. Now that list may be as small as nothing, such as here for the 7, Could also have a single item, which is nice because then we just like, well, that's the item they want. Or we could also have this massive list of 3 items in there. Furthermore, when you have more than one item, how do you know which one's the one that they want? So you have to make sure you store a copy of the original input. Now I'm doing that by default already, but you can see that why this doesn't work for passwords, because then you got to store the actual password in. So or at least you have to store some information so you know which of these is the accounts you want to use, the one for 42, the 32, or the 22. So again, throw away this for security purposes. This is simply for storage purposes. So let's think about the best and worst case scenarios. Best case scenario, no collisions, no need for lists. Everything has one item or no items. Awesome. Worst case scenario. Worst case scenario is, let's think about if I gave you a list that was this. Like that. Literally everything ending in 22. Same hash function, same hash table. What's your table going to look like? Literally just a massive linked list. If I can get this to turn. Wow, does not want to turn. Okay, now you're pissing me off. There we go. Wow, okay, it's just not happening. Let's just do it the long way. It just did not want to turn, you know. It's like you tell it to turn and it's like, nah, I'm good. Yeah. All right. So there you go. Now it's uh we got it. All right. So yeah, this is bad. So this is technically event time, right? Because it's a linked list. I started earlier by saying a linked list is event time. So we have lost all possible efficiencies. Why? The hash function's why. Could we use a better hash function? Oh yeah, we could have. In fact, we could just use something that takes the second digit. In this specific case, that actually would have been okay. And not have to make the table bigger. Or we could make the table bigger and make the hash function 100, right? So again, this all boils down to, do you have a good hash function or not? That's the first kind of big important thing. The second thing is, if you are going to have collisions, linked list doesn't have to be the end of it. We just learned about ABL trees. That thing at least can keep it in log n time. So you could use an ABL tree here instead. Now, I'm not going to build an ABL tree for you right now because that will take a while, but at least I'll build something that looks like an ABL tree. Uh, so probably it'll be something like 42 in here, 32, 52. Nah, so we probably actually want this one to be 22. 12, 32, and this was like 62, 72, 52, and a 2, right? So if we keep the information like this in here, so, you know, we make this pointer point to the root of that, then we can at least improve this to be log of n. I guess technically +1, but we don't care about that +1. So let's put it this way. You do an ABL tree like you've been doing, the best you can do is log of n. But even if you do a hash table with like the worst possible hash function ever, you know, it's gonna cost you 1+1 computation, but that's the worst case. In the best case, maybe you do use a good hash function and you end up with something better than log n. You know, maybe even constant time if you do a good hash function. But again, you're not at that risk because even if you don't, at least you got log n access time. So you can definitely mix data structures. And I do believe that when you use hashing in Python or other libraries, that it uses this log n ABL tree for collision resolution. If you use like if you know if you're using basically if you're using a dictionary in Python, That's where you use the square brackets, or sorry, the curly braces. So I can make that as a dictionary in Python. It's actually going to be using a hash table with separate chaining with ABLs. And that thing is pretty darn fast. So no downside to that, I guess, even if as long as you use an ABL. So yeah, and yes, OFN. But yes, we always pick the worst for the question on chat that said, so long as there is no null pointer, yes. So you always pick the worst, right? Because all of these are nulls, but that one's n. So we just say the whole thing is n because we always go for the worst case. So that's separate chaining. So now we can look at the formal definition. Say, almost formal. We say make each cell of a hash table point to another data structure, linked list, or ABL tree of record that have the same hash function value. Okay? So that's separate chaining, but it's also known as close addressing. Now, the reason it's known as close addressing is because even though you're doing this collision resolution situation, you're not changing where things hash to. So like 42 is always going to hash to 2 because that's what the hash function says. You're never going to find 42 anywhere else. Like you're never going to find magically 42 is here unless you're like me and you made a mistake when you put in the numbers. Like when I was trying to put 21 in the spot of 2, right? That means it's close addressing. Things must always hash to the spot that we say in a deterministic fashion. On the other hand, there is the second method of uh, of collision resolution, and that one is known as open addressing. And this is actually a group of methods, really. So what is open addressing? Well, that's literally what I just said, but opposite. So with close addressing, I'm saying that no matter what you do, you still put things in the spot that they should go to. So like 21 will always go in the spot of 1. Sure, we make a list here, whatever, a tree, but it's always going to go here. 55 is always going to go in this spot. You'll never find it anywhere else, so you don't have to worry about that. With open addressing, it's more like it's cool. If that spot is full, just look for another one. No problem. That's kind of what the mentality is behind open addressing. Okay? So unlike close addressing, all the elements are actually stored in the hash table. So we're not going to make any linked list or any ABL trees. It's all going to be in the array, basically. And you should be using an array because you want that memory access time. Now, there's different kinds of open addressing, and that's going to depend on how you decide where things get stored. So before I show those to you, and I'm not going to get through all of them today, I'm going to show you kind of what I'm talking about here. So let's take the same numbers that we had before, actually. In fact, let's see. Let's just take this whole thing. Oh, and by the way, 2 years ago, no, not 2 years ago, but actually 1.5 years ago, I did do a hashing class in VR, in Half-Life Alyx VR. I don't know, it's kind of cool. You're more than welcome to check that out on YouTube if you want. I do like the phone number example and all that stuff. The only issue was that it was kind of loud with the background noise in the game. So yeah, but hey, at least it was different. So I think that kind of gained some interest in watching it. So feel free to watch that if you want. More reinforcement and some entertainment, I guess. So okay. So what I'm saying is now we're back to storing the data inside like we did originally with the direct access table and all those things. So like for example, 42 goes actually in the array. So this is an array of integers. So you make the array of the same type as this rather than a pointer. Now it was pretty fun. Okay. So let's put the 8 in there. Very cool. 21 goes there. So yeah, I guess let's make this a pretty picture. put this in here because this is our black box. And the reason why I use this black box metaphor is because that's a lot of times how these hash functions work. Like you don't really know all the math that goes in there, and you don't need to. You just kind of let it happen. So that's why you kind of see that. But yeah, so I'm feeding 42 in there, and that says, yep, goes there with the 2. I'm feeding 8. That tells me, yeah, it goes into the spot 8. I feed it 21. That tells me, yeah, that goes into the 1, and so on. So like that, okay? But then I get to the 32. The 32 goes and gets computed into the 2 line 2, right there, right? So in this case, instead of making a list here and so on, what you do is you start looking for somewhere else where there's a spot available. Now, the most basic version of this is just to go down one at a time and find until you find a spot. So in this case, you first land on 21. You see, well, you first land on spot 1, and you see that 21 is there. So you're like, darn, what do I do? Okay, just go to the next spot. The next spot is index 2. You see that 42 is already there as well. You're like, well, I guess I gotta keep going then. Finally, you go to spot 3. You see that nothing's there. So you store your 32 in there. And you get to the 55, and you're good. You're like done. You go on, you feed in the 55 this time. 55 gets indexed to 5. There's nothing in there, so you're like, oh, great. All right, that one's easy. We just throw in 55. And then you're going to go ahead and you're going to put in the 22. That also gets you 2 in there. Of course, there is a 42 in there now. So did I say I again try to put it in the 21, but I meant in the 42. But yeah, so when you put in the 32, you know, you see that the 42 is there, and then you go down and put a 1. So you don't try to go to the 21, right? Same here. You feed in the 22. You see the 42 is there, so you try looking at the next spot. You see 32 is there, so you're like, oh, still full. You keep checking. Then you find the 4 is empty, and you put it there. And if you had to insert, let's say, like a 52, it would have to keep doing all these checks until it got to here, and then you put a 52 there, right? So you basically are just probing to see the next spot that you can put in there. This is what's known as linear probing. And it's the first of 3 methods of basically looking. The other 2 are, we'll talk about them next time, but they're quadratic probing, where instead of going in a linear fashion, you can multiply times 2 every time, so you keep jumping bigger and bigger, and I'll explain why that's useful next time. And there's another thing known as double hashing, which is just a fancy way of doing the probing where you feed it to a special formula. So like maybe instead of times 2, you times 3 it, or times 5, or square it, or whatever. This, of course, is going to cause a lot of issues for access time. In fact, your access time is just going to go, it's over. Like, I think it's going to be O of n, no hope. Even your insertion time is not going to be O of 1 because you got to jump around things. And like, your deletion time is O of n. So overall, in general, I'm not going to lie to you, open addressing is like, it sucks. But there is one good thing about it, and that is that it optimizes the use of it. So far, all of these, you've noticed that there's empty spots. And there's nothing we can get around with that. That's the cost of hashing. This is like, well, if you really want to maximize your hash table, but like not use a better algorithm like AVLs or something, then I guess this is for you. So it's not particularly useful that I've ever seen in real world applications, but we'll finish talking about it next time. But the one you should definitely know and it is useful is the chaining one that I first talked about, okay? So we will pick up from here next time and continue talking about hashing. I'll talk about rehashing. load factors, and these two other probing methods. And after that, we will finish. Okay? But uh, but yeah, it is hashing is definitely something that's very interesting and very relevant, but unfortunately very hard to explain with hash functions itself. So that will be on you if you want to explore it, but at least you know the basics for now of how hashing works. Okay? No, recurrences should not be in the next exam unless there's a recurrence related to one of the algorithms that we talked about. So, like, I guess like an ABL tree or something, but not like in general, like an overarching view. So, yeah. Again, sorry I didn't turn my camera on, but I'm still getting better. I feel better now, but like yeah, around the top of the hour mark, I started to kind of go down. I was like, oh no, I'm losing my energy now, but I'm better now. So thank you all for the nice wishes. Uh, so yeah, like I said, there's more videos on this stuff on my channel from previous semesters if you want to check them out. Otherwise, we will keep talking about this next week. But for now, wishing everybody to have a good weekend, and I'll see you next time. All right? Take care, everybody. Bye.